Let's start with a simple question. What even is a webhook? Imagine ordering food on an app. The old way computers used to check for updates is called polling. Your app would ask the restaurant server every few seconds, "Is my order ready? Is my order ready?" Over and over, 4 times, and still no answer. That's wasteful. Most of the time the answer is no, and you're burning server resources for nothing. A webhook flips this around. Your phone just waits. The moment the order is ready, the restaurant server pushes that information to you instantly, with 0 wasted checks. And webhooks are everywhere. Stripe uses them, payment completed, notify your store. GitHub uses them, code pushed, notify your CI server. Shopify uses them, order placed, notify your warehouse. Same pattern every time. An event happens, and a server pushes data to you. So here's how we'll build it. An event happens, it goes into a queue, a worker picks it up and delivers it to your server via an HTTP post. Event, then queue, then worker, then delivered. But here's the question. Almost no tutorial answers. What happens if your server, the receiver, is down? At that exact moment, the webhook arrives. Does the event just disappear? Today, we're building a webhook delivery system that solves exactly that, with automatic retries, exponential backoff, and a dead letter queue for events that fail completely. This is the core logic behind how Stripe, GitHub, and similar systems actually work under the hood. Here's the flow. Step by step. An event is created, it goes into a queue, a worker picks it up, and sends a post to the client. Success or failure? Now, what if we just retried instantly on failure? Imagine the receiving server is already struggling. We immediately fire another request, and another, and another. We're hammering a server that's already overloaded, making the problem worse, not better. Instead, we use exponential backoff. After the first failure, wait 1 second. Fails again, wait 2, then 4. Each wait doubles, giving the server time to recover, while still giving the event multiple chances to get through. Now, why does every event need a unique ID? Imagine attempt 1 actually succeeded on the client's end, but the response got lost on the way back to us. We'd think it failed, and retry sending it again. The customer gets charged twice. That's a real problem. The fix: tag every event with a unique ID. If the client sees the same ID twice, it knows I already processed this one and skips it. This is called idempotency. Finally, what if attempt 4 also fails? We don't retry forever. The event moves into a dead letter queue, not lost, but held for inspection. A developer can look at what went wrong, fix the issue, and manually replay it. Let's open our IDE. I am using VS Code for that. We have sender, receiver, and worker files. First, the sender. This is what your app calls whenever an event happens, like order created. We're using Fast API to expose an endpoint, and Redis as our queue. Every event gets a unique ID. This matters for idempotency. So if we retry, the client can recognize it's the same event. We also track the attempt number, starting at 0. We push it onto the queue as JSON and return the event ID immediately. The caller doesn't wait for delivery. That happens asynchronously. Next, a dummy receiver. This represents the other server, the one we're sending webhooks to. In real life, this would be Stripe's customer server, for example. It receives the webhook payload, and to simulate real-world unreliability, it randomly fails 60% of the time with a 500 error. In production, this might be a timeout, a crashed server, anything. Otherwise, it succeeds. Now, the core of this whole system, the worker. This is what pulls events off the queue and actually delivers them, with retries. We'll allow up to 4 attempts, with a base delay of 1 second. This is exponential backoff. Attempt 1 fails, wait 1 second. Attempt 2 fails, wait 2. Then 4, then 8. Each retry waits longer, so we're not hammering a server that's already struggling. This sends the actual HTTP request. If it returns 200, we're done. If it fails or even throws a network error entirely, we return false. And that triggers a retry. The worker loops forever, pulling events off the queue one at a time. If delivery succeeds, we're done, log it, and move on. If it fails, we increment the attempt count. If we've hit max retries, the event goes to a dead letter queue. It's not lost, but it's set aside for manual inspection. Otherwise, we calculate the backoff delay, wait, and push it back onto the queue to try again. Let's send a few events and watch what happens. First event sent, and delivered on the first attempt. No retry needed. The receiver responded successfully right away. Second event, same thing, delivered immediately on attempt 1. Most of the time, this is what happens. The receiving server is healthy, and the webhook just works. Now the third event. Attempt 1 fails. Worker waits 1 second, retries. Attempt 2 fails again. Waits 2 seconds, retries. Attempt 3 fails. Waits 4 seconds. And finally, attempt 4 delivered successfully. This is exactly why retries with backoff matter. If we'd given up after attempt 1, this event would have been lost, even though the receiver was perfectly capable of handling it just a few seconds later. Real-world servers have brief blips like this all the time: a deploy in progress, a momentary spike in load, a database timeout. Backoff gives them time to recover. If attempt 4 had also failed, this event would move to a dead letter queue instead for manual review. We won't trigger that here, but the logic is the same, just one more failure away. So that's the core. But what we built is a simplified version of what companies run in production. Let's zoom out. This is what we built today: event, queue, worker, receiver. Real companies add several layers around this core. First, rate limiting. Imagine one slow client is generating tons of retries that could starve all other clients' webhooks from getting through. A rate limiter caps how many retries each client can consume. Second, HMAC signing. Anyone could post a fake payment completed event to your server, so real systems sign every payload with a secret key, and the receiver verifies that signature before trusting the data. Stripe does exactly this. Third, monitoring and alerting. Picture your dead letter queue. 1 event, then 47, then 230. If that happens, an alert needs to fire and reach an on-call engineer, not get discovered 3 days later. Fourth, replay tooling. A dashboard showing failed events, their ID, their status, with a replay button. A developer fixes the underlying issue, clicks replay, and the event gets resent. This is exactly what GitHub's webhook delivery logs let you do. Companies like Swiggy and HookDeck exist purely to provide all of this as a managed service. But the core, the queue, the worker, the retry loop with backoff, that's exactly what you just built today. Same core logic, just more layers around it.